Are you Noel, Farah, and Kelvin? Okay, right, afternoon. Right, so today is Monday of week 10, right? So you can see that for our lecture, we are looking at quality of service concepts or QoS, right? QoS. So this is basically identifying different types of packets. The packets actually coming out from the OSI layer, application layer, right? Streams of data, right? So this data, depending on what application, okay, could be normal data like your email and stuff like that, right? File upload, download, websites you visit, but it can also be streaming video, like you're watching YouTube, or you're doing meet like this, like us right now, or basically doing VoIP, yeah, like calling people using Skype and such. Okay, right. So when we look at the needs of those applications data, right, we can see that some of those streaming data, some of them actually require different types of delivery options compared to other data. Okay, so this is where the quality of service comes in, right? Quality of service means we want to ensure, or uh, the ISP want to make sure, or even your own network lah, right? Your own LANs, or your own intranet. You want to provide guarantee for certain types of data. That means smooth streaming. So one way to do this is using quality of service. Quality of service will basically indicate which type of data that is traveling through the network needs to be prioritized. Okay, so this is the QoS concept. All right, so we'll start. We'll start. So I will start to record. All right, so QoS concepts is chapter 9. Okay, the topics we're going to cover, basically on the screen is shown uh, network transmission quality, different network transmission characteristics impact the quality of the transmission. That means here we talk about quality in terms of the what lah, the lag, or smooth delivery of data. Okay, so lag indicates there's a latency. There's a slow lah, basically. Okay, it could be determined by our bandwidth, and also there are many other factors lah, right? So our first topic is transmission quality, and then we also need to look at the traffic characteristics. That means the traffic is actually based off different types of data from different types of application. So certain application, we have a need of real-time transmission, near real-time lah, usually, right? So different types of application requires different priority for the data. The priority indicates during the transmission of those data, okay, how are they handled by the intermediate devices, right? So different requirement entails different way we deal with the traffic, yeah. And then, of course, when we do have bottleneck in our media, right? During our transmission, there's a bottleneck. Bottleneck simply means a place in the network where the traffic can be traffic jam lah, right? You can just say congestion, or you can think about it traffic jam lah. So when there is a congestion, certain devices, in order to in order not to lose any of the data packets, they have to have queuing algorithms. Okay, so we look at different types of queuing algorithms. Means you queue them in buffers, okay, before releasing them, okay, or waiting until available bandwidth is there before we can, resume to forward those data. So queuing algorithms, yeah. And then we look at different types of quality of service models, okay, right? And how it is implemented, okay? The implementation techniques. Right, so we start with network transmission, right? With that, I want to share with you the QoS, very short QoS, about 3.5 minutes. Okay, QoS, what is QoS, right? And why we need quality of service. Okay, always remember we need quality of service due to different transmission requirement for different types of transmitted data. All right, so let me just share.
QoS, what is it and why is it needed? QoS, or quality of service, allows us to prioritize certain types of traffic over others. Different types of traffic place different demands on the network. Video traffic and voice traffic require greater resources from the network. They require more bandwidth to achieve the type of quality that is needed in a phone call or streaming video. Financial transactions are time sensitive and they have greater needs than, let's say, a web page or regular data traffic like sending an email. In this diagram, we're given a general concept of how it works. Packets are buffered at the router, and three priority queues have been established: a high priority queue, a medium priority queue, and a low priority queue. Voice over IP traffic in the high priority queue is given a higher priority, so more of those packets are allowed to be forwarded across the network. Financial transactions, which are time sensitive are also given a greater priority, so more of those are allowed as well. And then lastly, any leftover bandwidth is used for the static web page in the low priority queue. When do we need QoS? We need QoS at points in the network where congestion is experienced. This could be points where you have an aggregation of many links, let's say many computers or many users, all having to go up a single uplink or across a single wire. Also, you can have situations where there's a speed mismatch. You're going from a faster link to a slower link. And also, as you cross from a LAN to a WAN, or from the WAN to the LAN, going from network to network across a gateway router. Without QoS, packets are processed as they come in, and when we have network congestion or variations in delay, which cause jitter, we experience packet loss. Now, if you're trying to stream a voice call or audio stream and you're experiencing excessive jitter or variations, the playout delay buffer can't tolerate it and packets are dropped due to that excessive jitter. Now, too many packets being dropped results in your call dropping out. Now, with QoS, more voice packets are processed or forwarded because they're in the high priority queue and it's been configured for zero packet loss. So you still have, let's say, variations in delay and you can have jitter, but an audio stream is able to make up for that, and a playout delay buffer can send out a constant stream of audio information, resulting in a call that experiences zero drop off.
All right, so that was a short video just explaining a little bit about QoS. Some of the terminology maybe I will explain further, like jitter or packet delay buffer. right? So let's have a look through it. The purpose of QoS is basically to prioritize traffic. So to ensure for a particular type of traffic, there is no it's always received smoothly by the end user, the destination, right? So because there are different types of traffic in terms of its priority, right? So you can see here, we can see voice, financial, web page as explained before. Voice usually happen in real time, all right? And when you expect to call, just like analog phone, yeah, we don't expect to lose any of the message you get from the sender to receiver, receiver to sender. So voice over IP needs to happen in real time. Therefore, we place a high priority on it, right? And financial transaction, well, although it is considered um, high priority, but it's not as high priority as a voice over IP. Excuse me. But it is still considered higher priority than normal traffic. Normal traffic is what we consider low priority lah. So if we experience delay in web page loading, it's not really as crucial as we have experienced delay with financial transaction, right? Some for financial transaction, we need to be able to record the transaction as it happens. So in a web app application, for example, or just think about ATM machine. ATM machine, yeah, you withdraw money, all right? So you need to be able to update, okay, the account of that person that is withdrawing the money, yeah, um, sort of as fast as possible. But a slight delay is still okay in terms of, if you think about it, maybe a delay of 1 second, 2 second is not that crucial. Okay, but for voice, if you every time when you're talking, like in the middle of my sentence to you, there's a delay like 1 or 2 seconds. It's very hard to have a conversation then, right? So this is one of the reasons. So simply put, higher priority get more packets, okay, sent through the transmission medium compared to lower priority, because we know the streaming data is segmented at the transport layer, right? So we multiplex those packets, okay, onto the same media where we do the transmission. So simply put, more packets of the high priority traffic, okay, it will be streaming through the medium compared to low priority packets lah. All right, so that's ensuring that when we receive, okay, the packets at the other end, right? For example, for voice over IP, more packets means more packets can be transmitted at any one time. All right. Okay, so here we talk about where specifically we can encounter congestion. Well, it's obvious here. There are three types. Three example here. Aggregation simply means multiple links carrying multiple stream of data converging into one particular device, and there's only one outlet. So you have many more input of data ingress compared to egress. So you will know for sure there will be a congestion happening here. So how to deal with this? Usually we put a buffer here. We put a buffer sufficient enough to buffer some of the data. So that we don't drop it. We buffer them, and then we release them into the converge link here at our convenience. All right. So another another case is, even though we have one ingress, one egress, but there's a mismatch in the speed of the media. So you can see the bandwidth for one gigabit. This one 1000 is equivalent to 1 gigabits per second. Is different from 100 megabits. So it's 10 times more capacity for this link, right? So that means the data they carry also is going to be needing 10 times more here. So that means, again, we have to employ buffer here to store or to queue those data, because we cannot physically deliver to the link 100 megabits per second link. All the data that we receive from the 1 gigabit per second link, right? Congestion will happen here. That means a delay will happen here because of the queue, the buffering. Okay. The third example is LAN to WAN or vice versa. This is because, again, it's the difference in speed. Okay. Typically, speed in a local area network is faster. Okay, faster compared to wide area network. So the transition between LAN to WAN will also cause congestion, right? So you'll find that there will be a delay, a latency here caused by the buffering here. All right. So these three examples of where congestion can happen, right? So think about it. When you for every intermediate device, you have to consider these types of transition. So you can see that it all add up, yeah, between the source and destination. It will all add up. The more device you have, or the more transition you have between mismatch of speed, or also aggregation, then the more delay that you will face, right? So let's talk about bandwidth, congestion, delay, and jitter, right? So talk about jitter first. Jitter is basically the arrival of packets at the destination, right? So when we talk about jitter, let me just briefly talk about what this jitter is. So jitter is the arrival of packets as close to the destination, but it is not arriving in a orderly manner. So there will be sometimes it might arrive steadily. Steady means one packet, one packet, one packet. It's regular, but then sometimes it can come in like multiple packets. Okay, in short period of time, right? And when that happens, it's possible. It's possible that the buffer, okay, which is what just now we talk about um, the buffer that we were talking about here is let me just move forward quickly. The play out delay buffer, which is used to buffer the incoming packets, right? So when that happens, when it's full and it cannot cope, then it has no place to put the still incoming packets. Therefore, the packet will be dropped and it will be lost. So too many lost packets, is usually cause the data received as failing to receive data. So for TCP communication, where it's guaranteed, then too many drop packets will cause in error, right? Because it's doing retransmission, but you keep dropping packets, then the transmission will be stopped, right? So this is the consequence when we have jitter, right? So let's talk about delay. The different types of delay. Code delay, when we talk about code delay, means it's at the source, right? The code delay is the part where at the application layer, we are doing the compression of the data, right? So that means if you're real time sending out a stream of data, whether it's video or normal data, that needs to be compressed. okay, the compressing of that data needs some time, right? So before it's actually go out of your NIC, your network interface card. So we still need time to compress data. Compressing data is very normal for transmission, because compressed data means you need less bandwidth to carry the data. Okay, reduce bandwidth to carry the data because the data becomes smaller. But the compressing of the data introduce a delay. We call that code delay, right? And then as the data stream, compressed data stream, perhaps goes down the OSI layer, application, go to transport. At transport, it's segmented, then goes to, for every layer after that, network, and then data link, you need to do encapsulation. And of course, the reverse at the destination, de-encapsulation. So the encapsulation of the packet, where you put in all the necessary information to allow it for it to be delivered successfully. Remember the info that you need to write into the header, okay, of the packet. That introduced delay as well. So that delay is called packetization delay, right? And then once it reached the before the physical layer, the data link layer, right? And before that, it will turn into bits, encoded into bits, and for transmission through the media, it will be put in a buffer. Why? Because the packet or the frame, okay, if you talk about it in layer 2, is waiting to be transmitted onto the link, to be put onto the link, right? That also introduce a delay, and it's called queuing delay, right? It's queued up there. Each of the packet or frame waits to be put onto the link, to physical link, right? Now, while the packet or frames is traveling, right? Sorry, before that, that's propagation. So before it's traveling through the media, right? To transmit the frame onto the physical wire itself is called serialization delay. Then after that, as the packet or frame is traveling between source and destination, right? We also observe that it will take some time for that particular packet to arrive at the destination from the source, right? So that kind of delay is called the propagation delay, right? As the packets reach the destination and it's being received by an destination NIC, and it's being put into the buffer, right? Then we call that the Jitter delay. The Jitter basically means, hang on, I guess. Right, so digital delay is the fixed amount of time it takes for buffering a flow of packets and then sending them out in evenly spaced interval. Basically, if you are because due to whatever is happening in this delay here, especially in propagation delay, since packet non-deterministic, I mean it can basically be forwarded between different paths on the internet, for example, right? So the maybe at the time where the packet is transmitted, it's actually evenly spaced out. You know, you time the submission of the, or the, the placement of the packet onto the link in a very well mannered time interval. Okay, but due to the different route or different device it encountered during its propagation, then you might have a delay in some of the packets. So that means arrival at the destination is not ensured to be evenly spaced, right? But the thing is, when you want to present the packet back into the application, right? Instead of presenting the data in like uneven space interval, you want it to arrive at the application layer at evenly spaced interval, so that it can be processed continuously in a nicely timed manner. So you need to de-jitter it. So jitter means arrival in uneven space interval. So to de-jitter means you buffer it first so that you can control how you pass that data back to application, mean in an evenly spaced interval, right? So it's no longer in bursts of packets, right? So these are the different types of delays as packets being transmitted from the source to destination. All right, so here we talk about packet loss, and this packet loss is due to the buffer, right? The buffer unable to cope with the incoming data stream, right? So think about if we don't have a quality of service mechanism, a way to prioritize and also to choose delivery, okay, of packets. There are some time sensitive packets such as real-time video and voice, right? That may not be able to be caught by the playout delay buffer, right? Or either is too many arrive at the same time or too little arrive. Okay, so but here we deal with too many arriving at the same time, right? Okay, so basically we already seen that this play out delay buffer is able to compensate for the jitter. We talked about jitter in the previous slide, yeah, right? So usually this play out delay buffer so that the incoming packets, although they arrive not in a evenly spaced manner. You can see here the space arrival is not evenly spaced. You can see here it's shorter, longer time between arrival, slightly longer time, and short, right? But what we want to do is when we present it to the um, to the to the upper layers, right? So we want it to be this way, or this can be at the destination, yeah, can be at destination, or it can be at intermediate device, right? It depends where it's implemented. But the target is for the playout delay buffer is to queue all these incoming packets, and then release them again in a more evenly spaced interval. So you can see here the intervals are all evenly spaced, right? This is the purpose. Okay. Right. But if the jitter is so large, right, and that means when because it's not coming into the playout delay buffer, the stream of packets are not coming in nicely, Sometimes very few arrive, sometimes not at all, sometimes suddenly a big burst of data coming in, thereby overwhelming the buffer. Means buffer is not able to store it, yeah. Then there's no place to put it. Then the packets we call out of range packets have to be discarded or dropped, right? So in terms of experience, if we are talking about audio data, right? That means some parts of the audio is not there, right? It's just lost. Okay, so if it's not too bad, that means the loss of the packets is very minute. That means a small amount. The digital signal processor of your audio, okay, audio processor in your computer will be able to predict, okay, the in-between signal. So basically interpolates here means the DSP is thinking about, okay, so this is the audio stream, audio packet, and then the next one is here, right? So in between, rather than just blank or just combine them together, of course, it will be very abrupt, right? If you just combine them, because certain loss of data means certain part of my voice, for example, I'm talking to you guys, will be lost, right? So if you just connect them together, it will be I'm saying something suddenly, I'm on a different sentence or different word. Okay, I'm in the middle of talking about something. Maybe I'm saying a word. It could be between words. One word is lost, or some sound in middle of the word that I'm talking about is lost, right? So if it's small packet loss, that means the DSP, based on the current data it has, it can predict what is the data should be between two packets. Okay, so example, one packet, the DSP can generate, based on the, let's say, for this packet, if this packet is non-existent, the DSP can look at this packet and look at this packet, can predict or guess lah. There's some kind of formula to do that, to put in the intermediate audio signal, right? If that is small enough, so it's not so jarring to the user when the user is listening to the audio. But if the jitter, thereby the data loss or the packet loss is so much, for example, instead of one packet loss, we have multiple packet loss in between. So in fact, even looking at the at each end of the loss of packet, the DSP do not have enough information to interpolate or regenerate some of the signal here. Remember, the signal is created based on assumption by the DSP, based on the both end of the audio packet. Okay, just guessing. Okay, guessing. Okay, of course, there's a formula lah. Guessing. Okay, I think this audio signal should be like this, based on the audio signal on the left and right. Middle one should be like this. But if the loss is so big, even that is not available for DSP to do lah. There's not much the DSP can do, right? So when the jitter exceeds what the DSP can do to make up for the missing packets, we actually hear audio problems. That means skipping. For example, when I talk, there's something like I skip to something else when I'm talking, right? So you miss out on maybe part of my what I'm saying, and then suddenly I'm already talking about something else. So these are audio skipping. This is all caused by jitter. Okay, the jitter is too big. All right, so now let's talk about traffic characteristics. So traffic, data traffic, and what type of characteristics we have in the data traffic, so we can categorize them. So again, let me show you a short video of that.
Voice traffic and video traffic place a greater demand on the network and are two of the main reasons for QoS. There are some differences, though, between voice and video. Though they are both demanding, voice packets do not consume a lot of resources because they're not very large and they're fairly steady. So the characteristics are smooth and benign in regards to the demand it places on the network. However, voice traffic is sensitive to drops and delays and therefore requires prioritization. Packet loss should be no more than 1% with voice traffic, and voice traffic requires at least 30 kilobits per second of bandwidth. Now, video traffic is more demanding. The size of the packets that it sends across the network are more bursty and more greedy. It consumes a lot more resources. It's also sensitive to drops and sensitive to delay, and it requires no more than 0.1 to 1% loss of packets. and requires at least 384 kilobits per second in bandwidth. In this next graphic, you can see some of the differences. You can see that the audio samples of voice packets are fairly consistent at 20 milliseconds per sample, and the size of the packets are very small. However, video packets, depending on the frame of video, if there's nothing changing in a frame, then they might not have a lot of size. But if there's a lot of action, let's say in the video or in the movie, then the frames are going to be very greedy or very large. So you can see that it places a greater demand on the network. Data traffic is different from voice and video traffic in that it's generally not as demanding. Also, a lot of data traffic is sent with TCP applications, which can retransmit and are therefore insensitive to drops and delays. There are different types of data traffic. There is mission-critical data traffic and non-mission critical data traffic, interactive traffic and non-interactive traffic. If you have interactive mission-critical traffic, like in bank transactions or purchases, then there is the expectation of a quick response time in the data. However, a lot of traffic is not interactive and not mission critical, let's say a standard web page, and can therefore be the least prioritized. Large, and they're fairly steady. Sends across transactions or purchases.
Oops, sorry, I'm on mute. I talked so much already. Sorry about that. So I was talking about the different type of voices. Just now, when I was explaining, did you guys hear about the difference between the voice and video traffic?
No.
No, right? Right. So I was talking about in terms of voice. Okay, the voice traffic is very regular. Although the requirements for voice and video are almost the same, right? Because we cannot tolerate data loss because for voice, if too much data loss means I'm skipping. You miss some of the parts of the message that I want to say. Video is the same. You miss certain scenes, right? So both of them actually needs as few data loss. I cannot really tolerate that. But the difference is this in terms of the regularity of the transmission of voice and video data. Voice data, is a conversion between analog signal. Analog signal is continuous. Okay, we have to transform it to digital. In order to transform, we need to basically sample as much as possible, depending on the resolution of the voice data, audio data, right? The more samples you take within a second, right, the better quality you can hear about the audio. Okay, but you can adjust by the sampling. But once you sample, you can predict because the sampling is regular. Sampling of the data for audio is regular, so it's not so bursty. Bursty simply means you get a regular amount of data, suddenly you got lots of data, then go back to small amount of data, regular amount of data. So there is a burst. For audio, it's not so much. But for video, yes. We all know, right? Video is made of frames. A frame is basically an image, right? Okay. So in a second, how many frames is inside that video. So that's why the traditional one is about 26 point something frames per second, but nowadays we can stream 60 frames per second video, right? So the more frames per second, the more data you need to transmit. Okay, we're not even talking about resolution yet, but still frames and resolution are regular. But how do we transmit video? We compress them first, just like audio. But difference with audio, because audio data is regular, so compression also regular. That means data produced, the amount of packets produced for audio is the same. But for video is different because the compression rate changes by what it needs to compress. So the compression works on each frame. Imagine each frame is an image, right? So depending on what is on the image, then the compression ratio either is very good, very high. That means you can compress the data so much, so very little data is needed. So this is if you look at the image, it's very regular, like blue sky, duck scene, because there are so many similarities in the image, in the frame, that when you compress, it's very good compression rate. But there are certain scenes, action scenes, like what the guy said. A lot of things going on. There's so many things in there. The compression rate is not that good. So more data needs to be transmitted because less data is compressed. So for those kind of frames, those scenes, then suddenly the data transmit is a lot. Then that's the burst of data. Suddenly followed by, normal scene, not much going on. So, okay, the data packets is, one by ones. Suddenly, action scenes, right? Compression not so good. So a lot of data need to be transferred. So that's the burst part. Okay, so that's the difference between video and audio, or video and voice, right? All right, so that's what we call by burst. Okay, burst. Suddenly a lot of data coming in, but then after that, not so much, and then a lot again, right? So we want to talk about now. Video is the most consumed data among all internet users, right? So I just want to share. Hang on, let me just share this info, even without considering about the trend of usage. In fact, we can see during the pandemic, right? During the pandemic, what happened? All the all the ISP have to suddenly adapt to this, because suddenly, because of the pandemic, we work from home. Okay, let me just share this info with you guys. You can have a read of it. Okay, you can see that in the article, it says rise in video consumption. Nowadays, it's not enough already. Social network, just text. Now the most popular ones are like Instagram with video and TikTok, right? So you can see here. Okay, this all contributes to including Netflix, Prime Video, Disney Plus, Max, all this video streaming online also contributes to it. So what will happen? Please read through this to read further. This cause, video traffic becomes the main traffic that is on the internet. There are other traffics, but now a lot of the traffic is composed of video. So this QoS, in order to provide all this capability for the network to transport video traffic, is becoming more important, right? You can think of in the future even more. Okay, even more video will be traveling through the network basically. So you can see here, video traffic is at 2017 is 70%. Just now the article I gave you quite recent because it include the pandemic situation. So online game, yes, you can think of the online game if it's generated, okay, generated like a cloud, like Google Stadia. Microsoft also has started to do this, where you don't depend on your computer anymore to do the gaming, right? So you know, as long as your computer is able to maybe produce the resolution of the video, all the computation is done at the server. What they do is this: you stream what you're doing to the cloud stream back, okay, stream back the video to you. The video is what is going on in the game, right? So that consume a lot of data. But if you're hosting the game in your computer, basically, when you say consumer data, it's not really compared to video data. Once you start cloud gaming, that means even your lowly tablet or phone can run Crisis. You know, Crisis is one of the most hardware demanding game, right? But it's now running on their computer, on their cloud computer. Imagine this: all the computation is done at their site. You're just basically seeing the video of what you're playing. It's not really video, right? But it's streaming to you, right? It's streaming to you as if it is video, including audio, video, and your your controller, you control in your machine. So cloud gaming. So I'll just give you example. Cloud gaming. So it is the trend right now. Okay. Best cloud gaming. Cloud gaming will demand more of the network, right? Because you don't need to buy all the hardware anymore. You subscribe to the cloud gaming service, and whatever kind of game, no matter how powerful, right, it will be done by their servers, right? So what you get, as long as you provide, let's say your monitor is 4K, so you're streaming 4K video, like it's like as if video, but controllable video, interactive video, because you're playing the game. Imagine your computer, you just put somewhere, right? And then via the network, you play the game. So that's cloud gaming. All right. So yes, online game, not the current multiplayer game. The current multiplayer game just send basically all the information needed, okay, but think about it. If you, let's say you're playing first person shooter, okay, the details that the other player needs to know, or the server that you hosting your game need to know, is your location, okay, and then you need to stream back other people's location, right? And any object, whatever that's changes in the game world that affects your view of it, it needs to be transmitted. But it may not be video images, because those video images or your real time, okay, video creation is done locally. So compare between cloud gaming and current multiplayer gaming. Multiplayer gaming currently, you consume less data compared to cloud gaming. But why will people want to do cloud gaming? Because then they don't have to worry to buy the latest RTX or GTX kind of video card that is costing, like, to get the full benefit, like 4 or 5K worth of gaming hardware, right? Okay, so instead you just basically subscribe to the cloud gaming, then you can play as long as you get very good bandwidth. Okay, so that's the future of gaming, the way I see it, right? Of course, you're not going to replace current gaming right now, because I think developers need to support cloud gaming, features, okay, and also bandwidth have to catch up first. But if you can get Netflix 4K Ultra HD, then should be no problem, right? If your bandwidth can support 4K. movies, I think there's no problem. Right? Is that okay, Farah?
Okay.
Yeah. All right. So here talking about network traffic trends is video, video, video. Okay. Now TikTok very popular. People like to share video, streaming video. YouTube, you know already. Okay. Everyone use YouTube streaming, consume from YouTube and other streaming service as well. Right. So as I mentioned before, the the technology behind voice sampling, yeah, means voice traffic is predictable and smooth, but it is very sensitive to delay and drop packets because once you get delays, then you have to wait for me, for example. So you're listening and then suddenly 1 second delay. That means 1 second you didn't hear anything. And it's kind of awkward if you're having conversation when you have delays, right? Okay. Drop packet simply means I can simply skip. Like for example, let's say I read something. Voice packets must receive Cisco products use the RTP port, something like that. You just don't have the information because it's lost, right? The information is supposed to be voice packets must receive a higher priority than other types of traffic. Instead, you get this: voice packets must receive the RTP port range 163. Those information that is supposed to be there is dropped, is lost. So you don't have info. So that's why it's sensitive to delays and drop packets. Okay, so voice packet also must uh, have a higher priority than other types of traffic just simply because of these two problems. Of course, the video also sensitive to delay and drop packets, right? But compared to voice, is not predictable. It is not smooth because of the bursty nature of videos, right? Different scenes in the videos will produce less or more data. So the more data will be the burst of data coming in, right? Compared to the normal, maybe the video, right? Maybe the scene is very serene, very regular, the image, less compression, more compression can happen, so less data arriving. Suddenly, very messy image, compression rate drop means more data needs to be transferred. Okay, so that's bursty, right? So this is the voice characteristics, smooth, benign, means demand on the network because it's predictable. It's not that bad compared to video. But in terms of packet loss, it must be, it's still sensitive to packet loss. So less than or equal to 1% only, or else that's it. The quality of your audio will drop and even maybe disconnected, right? So here UDP priority is using UDP priority implementation of priority on UDP. UDP means if you drop, there is no getting back. There's no transmission, retransmission because it's not connection based. It's connectionless UDP. Remember transfer layer, the transport layer. Sorry, transport layer. Okay, these are the specification lah. Basically, latency should be no more than that. The delay lah, 150 millisecond. Jitter should be no more than 30 millisecond. Packet loss no more than 1%. You need to have at least 30 kilobits per second of bandwidth. But this one is easily achieved, 30 kilobits per second, right? So now, even with maybe you're like you subscribe to Tidal, like Spotify, Tidal, they got the very high quality compared to the highest Spotify can give, right? For audiophile, they want higher and higher because maybe the equipment is able to reproduce those kind of quality and sound. Yeah, hi-fi. So they demand. So that means yes, for audio at that quality maybe needs higher bandwidth. Okay, because more data is needed you know to encode higher quality audio. But for in general, voice traffic that you can hear me, maybe it's Twitter, it says here, minimum 30 kilobits per second is okay already. But compare that with video. Video is unpredictable because of the content of the video. Like I say, there might be very smooth frames, smooth scenes in the frame, and then suddenly you've got messy scenes, many things going on. So compression rate go up, down. The changes in the compression rate because of its ability to encode those different scenes means also the rate of data being transferred go up and down, go up and down. So it's unpredictable, it's inconsistent, and it's bursty. Okay, so compared to voice, video is less resilient to loss and has a higher volume of data per packet, right? So you can see here bursty, greedy. Greedy simply means it will try to gobble up your bandwidth. So imagine if you have just so and so bandwidth, and then one of you watch 4K, uh, Netflix, another maybe you have another TV in another room, then your friend or your siblings or whoever you live with also want to play 4K video. So suddenly, your requirement, maybe your bandwidth cannot support already. Okay, so because it will then when someone is making full use of the bandwidth for video streaming because it's a higher priority, then other bandwidth, remaining bandwidth is less now for other internet usage. Okay, right. So video also use UDP, no retransmission. Right, so data application that have no tolerance for data loss, like we talked earlier, is about the maybe ATM machine transaction, online banking, things like that. So email, web pages all use TCP. TCP needs retransmission, right? So if there's packet loss, it will try to retransmit. Okay, so data traffic can be smooth or bursty. It depends on the application, right? But network control usually is smooth and predictable. So TCP application can consume a large portion of network capacity because of the TCP retransmission, right? Because of the need to be reliable, so that means it will retransmit lost packet. Then a lot of times you're sending the same packets over and over, right? Okay. And also example like some application like FTP can consume, you can actually network share via application. Application is the one controlling the use of the bandwidth. Some application allow you to do this, especially file transfer programs, right? So ensuring, right, you can allow a little bit of bandwidth for other things. Okay, if not, if you would say use the whole bandwidth, it can use the whole bandwidth. It will take over the bandwidth. It will try to utilize. Why? For certain um, FTP will make full use of the port that you assign for data transfer. So like monopolizing the bandwidth. For other download programs, some modern download programs, they can open multiple connection to the same download file, right? And then can specify at which point of the file they want to download and how what's the size. So basically, if you say use full bandwidth, you open up, you can allow like 10 connection per download, then it will open 10 connection, divide the file to 10 segment that, and then each download will try to download that particular segment at the same time. So basically it's going to take over the entire bandwidth, try to accommodate 10 separate lines to download. Okay, that's why some file transfer, some downloading program work very fast. It's not magic, it's actually they're opening up multiple connection to this to download the same file, and they download different piece of the file at the same time, right? And then when it reach your PC, then they try to combine them. This is at the application level, right? All right, so even though some data traffic is not sensitive to drops and delays, like example, you're opening a web page or reading Wikipedia, whatever, it takes its time to load, right? But still, a delay too long will interrupt your quality of experience. Okay, so if it delay too much, okay, you will also feel like, oh, this is too laggy, right? Your web page opens so slow, right? So even though it's sensitive, we still try not to impact too much lah. So we want to still provide a quality of experience to the user. Okay. Now the thing is, data can be even more categorized between interactive, not interactive. Interactive means if you are interacting with the, let's say, web application, you interact with the application. Interactivity means very quick in response time. That's why a lot of the interactivity is done locally. Think about web app development. You're using JavaScript, right? JavaScript to provide interactive capability. It's done locally and the client side at the browser, isn't it? That ensure, because the back and forth between your web client and the web server might have a latency, right? So for interactive, one way they do this, right, application level is, oh, we can use JavaScript at the client side to provide immediate interactivity, okay, as much as possible, right? So reduce the need to go back to the web server and come back to the web client again. But let's say you don't have that facility. Interactive means you do interact with the web server. Then you, if it's interactive, you need to provide quality of experience. So that means you have to limit the response time also between 1 to 2 seconds. I think it's acceptable. Beyond that, then people start to notice the lag, right? Okay. But if it's not mission critical, then I guess it's okay, right? You don't, it's not mission critical, so you can tolerate, even though maybe your quality of experience maybe impacted a little bit, but well, it's not mission critical. It's okay. Non-interactive, even better for in terms of utilizing the remaining bandwidth, right? So delay can be different depending on available bandwidth, but you still can accept it lah, right? Okay, as long as the necessary minimum bandwidth is supplied, then it's okay for you. That means it still work, but it's not interactive, so you don't expect immediate response, right? So email, when you send an email, it's not interactive. You don't expect to get a response from your email immediately. So the email server transporting your email and until the destination is not mission critical, right? It's not interactive. So you don't really care about, oh, my email must be delivered now. Of course, if you want to, if you want that, then you choose a different application. You'll choose instant messaging rather than email, right? So this is considered as non-mission critical. All right. Any question?
No.
No. All right. So we're going into the next one is actually queuing algorithm, QoS algorithm. So we have Fifo Queueing. Fifo Queueing is basically first in, first out. So like first come, first serve lah. Absent, there's no quality of service for that because it depends on who first, then it will be served. So then we have weighted fair queuing, class-based weighted fair queuing, low latency queuing. So let me also share.
If we look at the queuing strategies for QoS, Fifo queuing, or first in, first out queuing, is basically the absence of QoS. In other words, packets that enter the router leave the router in the same order. Compare this with QoS and weighted fair queuing, or WFQ, and packets that come into a router, let's say, are then classified and prioritized based on the classification. So high classification packets are prioritized when they're sent out of the router. A newer form of weighted fair queuing is class-based weighted fair queuing, where specific classes of traffic can be configured by the administrator and used to prioritize different types of traffic. In order to guarantee that voice traffic is prioritized to the point where there's no drop-offs, low latency queuing can be used with class-based weighted fair queuing to prioritize voice packets above all else, ensuring that voice calls will not drop off. The example you see here is a combination of low latency queuing, a priority queue, in combination with class-based weighted fair queuing to achieve that very result.
All right, just now you watch just a brief example or explanation about FIFO, WFQ, CBWFQ, and LLQ. So it's aware to put priority on a different type of data. So we see that FIFO is the one without any QoS at all because it's first come first serve. That means it will be forwarded as the packet entered, right? There will be a queue, but the queue is based on first come first serve, or first in first out. The rest, basically, you put them in a queue on their own, depending on their priority level. Okay, so let me just, all right. All right, so the QoS policy can be set by the network administrator. So putting which kind of traffic has a higher priority can be determined by the network administrator, right? So queuing is a congestion management tool, right? That can do buffering, prioritizing certain class of data, and if needed, reorder the packets before it is transmitted, right? So inside the router, as data comes in, it's sorted, right? Based on priority, based on class, special status of priority queue. For example, voice data. Right, so first in, first out, very easy, no quality of service because you can see here, based on the color indicates the arrival of the data packets. And then it enters the router and then it's just being sent out as it enters. No change, right? All data is treated equally. Then we have weighted fair queuing, right? See, this is automated also and provide fair bandwidth allocation to all network traffic. So what it does is it applies priority or weights higher. I believe higher weights is given high priority to traffic. So it means you need to identify traffic. You need to be able to identify the traffic. In this case, actually, the bits that is values are put inside to identify that traffic. So when they read the header, they read that field, they retrieve the information there, and they can then say, oh, this data is belong to which priority. Okay, so and each of them are given a queue, right? So traffic belonging to the same priority or weights will be put into the same queue. And then the allocation of the bandwidth is given more to the higher priority compared to the lower priority queues, right? Then we have class-based weighted fair queuing. It's improvement, right? So basically, the traffic classes is created based on matching criteria that looks at protocols used, access control lists, remember ACLs, and input interfaces. So you say, prioritize, traffic incoming from this particular interface, for example, right? So if a packet match any of the criteria given this criteria, then you can also set. Then it then allocate to a particular class for that particular traffic. Okay, so in that class itself, okay, then there's a Fifo Queue. This Fifo Queue is per class. Okay, per class. That means if you want to, let's say that here class, then the priority inside each class is based on FIFO, first in, first out, right? So there's no reordering inside each class, but you divide the traffic into classes. Okay. All right. So there's a problem here that we have to discuss, which is the queue limit. This is basically limited buffer size. The RAM, okay, usually limits the size of the queue. So if the queue is full, the buffer is the queue is full, basically there's no place to put already. Then the tail, because it's a FIFO, each class is a FIFO. Okay, the head of the queue is here in terms of FIFO. The tail will be at the incoming end of the queue. So the packet that cannot fit into the queue anymore will be dropped, because this is tail, this is head. In the queue data structure, head, tail. That's why it will drop here at the tail section, tail drop. Or we can also say it's a packet drop. Okay, tail drop simply because it's at the tail end of the queue, right? So this is what happens, right? So the tail drop happens equally, right? I'm not going to, if I'm going to drop a packet here, I'm not going to, here still maybe got space, right? Well, I'm going to say, oh, maybe, hang on, maybe it's not that way. Maybe here is full, high priority, right? And got no space, but I noticed class 3 still got space. I'm going to put there. No, because it's equal treatment, right? All traffic equally is treated equally. It means if it's meant for class 1, the packet, no space already in class 1, this will be dropped, even though there's space in class 3. Okay, because class 3 is only for class 3 traffic. So this is what it means here. Treat all traffic equally does not differentiate between classes or service, right? Then there's a special queue that overrides the other classes, which is the class priority queue, the priority queue. Yeah, here again for Cisco, this is reserved for voice packets. Okay, always get the high priority from any of the classes, right? Inside the classes, then depending on classes, which priority you give, right? Then that class will have the that priority. But priority queue here will always get high priority. So voice, for example, get priority from all other traffic. Okay. Okay. So now let's look at QoS models. Right. So I'm going to show you the video for that as well.
In a very general understanding of QoS mechanisms, let's first look at the QoS models. The best effort model is not really an implementation of QoS, as packets are delivered on a best effort basis, and QoS is not really required or configured. The Integrated Services Model, or IntServ model, provides a very high degree of QoS to IP packets with guaranteed delivery. It uses a signaling process known as RSVP, or Resource Reservation Protocol. The IntServ model can severely limit the scalability of a network, and it is demanding on resources and therefore doesn't scale well for large or enterprise networks. The Differentiated Services Model, or DiffServ model, is a highly scalable and flexible implementation of QoS. It works off of manually configured traffic classes, which need to be configured on routers throughout the network. If we look at some of the benefits and drawbacks of the best effort model, you can see that under benefits, no special QoS mechanisms are required, and it is the easiest and quickest model to deploy. However, under drawbacks, notice that there are no guarantees of packet delivery. No packets have preferential treatment, and critical data is treated the same as casual email is treated. Basically, this is a non-QoS solution. Now compare this to the Integrated Services model, looking at some of the benefits and drawbacks. Under benefits, you can see that the IntServ model has tighter QoS for real-time traffic, uses the signaling protocol RSVP, Resource Reservation Protocol. It requires end-to-end signaling and per-request admission control. It uses packet classification, policing, queuing, and scheduling. Under drawbacks, notice that the IntServ flow-based approach is not scalable to large implementations such as the internet, and the integrated services model is rarely deployed by itself alone. Looking at this diagram, we can see that end-to-end signaling is required in the integrated services model. RSVP is implemented on the routers within the network and can be implemented on the hosts as well. Notice the QoS-aware nodes. Sessions and resources are dynamically reserved one flow at a time. Now, looking at the differentiated services model, we can see some of the benefits and drawbacks. Under benefits, the differentiated services model provides better QoS scalability. It is a defined class-based approach, defining the policy and priority at the routers, known as per-hop behavior, or PHB. It uses packet marking directly in the packets. In other words, packets are marked at the routers. It can also use the NBAR or NBAR2 network-based application recognition services. It uses the 6-bit differentiated services code point, or DSCP, in the IP header, and is also used with IPv6. Under drawbacks, it doesn't provide the absolute guarantee of service that integrated services does, and it requires a set of complex mechanisms to work throughout the network. This is why differentiated services is often used with integrated services. Both the integrated services and the differentiated services models are not exclusive, and they can be used together. In this diagram of a differentiated services example, you can see that the QoS nodes are unaware that QoS is being implemented across the network. That's because a manual QoS policy has been configured on the routers in the network. Notice that as traffic goes across the network, the traffic is classified and colored.
All right, so that was a brief explanation of QoS models. There are about 3 of them: best effort, integrated, differentiated. Right, so let's look at this summary here. Okay, so the model here, we have best effort model. Basically, best effort model is standing on its own because this model is actually a model where QoS is not configured. That means it's not even considered. Right. So excuse me, 2 minutes, yeah. All right, so I'm back. Sorry about that. So best effort model basically is a model where there's no QoS, right? Okay, so basically, if you want to do any kind of guaranteed delivery, or you have traffic like voice or video, basically you can only hope for the best. So that's why it's best effort model, right? If there's suddenly latency in the network or so many other data need to be streamed, then uh, it will, of course, the performance go down lah, right? So best effort model. So for best effort model, you have to depend a lot on the bandwidth available lah, right? But these two, integrated service and differentiated services, they are based on QoS, but they differ in a way that they are implemented, right? So integrated service, because the host communicate with the other host. Okay, so let's say I'm delivering a voice. Okay, I'm talking, I run an application, I'm doing VoIP. So my host will have to talk to the other host to signal, okay, now I want to start a voice over IP communication. Therefore, it works, how to say this? It works via one session by one session. So if one session is separated from the other session, right? So the other session independently will have to connect to another host, a different host maybe. And then what happens is the priority will be given to this kind of application, like voice application, right? At the expense of other traffic, lah, right? We say guaranteed delivery. Let's say for VoIP, that's our policy. We want to have guaranteed delivery, right? So in this manner, it says here, scalability is limited. Why? Because you cannot, basically, it's very hard to scale. Scale in terms of, if you have one conversation, right? Voice conversation, there is one, one signal, right? One session. Then if you add more and more and more and more session, just in case in your network, a lot of people certainly want to have, conversation using VoIP, then the performance degrade, right? Because this is why it says limit the scalability of a network in terms of providing that kind of service. Differentiated service offer a different way. It's basically built into the network itself. So there's no need for the host to contact another host. Okay, I'm going to start doing VoIP. What it does is it provide a tag inside its header to indicate that this packet is actually a priority packet. It's a some kind of priority packet. So it is up to the routers or hops in the middle, okay, that connects between the source and destination to decide how to do the, forwarding, the path, and so on, in order to provide, best services lah, quality of service. All right. Right. So best effort model benefit is scalable because, well, there's no QoS, so best effort, right? So if you increase the type of traffic, then you can, no problem. You don't have to reserve any bandwidth. But again, this is best effort. Of course, it will go down. Not to say that when you scale up, if you don't improve your network capacity, then it's okay. You still need to consider that if you scale up. But because no expectation, right? Best effort only, right? So you can see scalability is limited by available bandwidth, meaning to say if you predict that your VoIP application is going to increase, you need more bandwidth, then you have to upgrade your bandwidth, right? That's all. So there are nothing to configure because no special QoS mechanisms is used, right? So basically this is the default, right? So this is the easiest and quickest model to deploy. No guarantees of delivery because, well, there's no quality of service. Packets will arrive when they can in any order possible if they arrive at all, because it can be dropped. No packets have preferential treatment. There's no classification for the type of different packets, right? So critical data is treated the same as in the other non-critical data like email, okay? So integrated service, you have to, if this is your host, you want to communicate with this host, send VoIP communication, you need to contact this host have a session with you, and throughout this session of VoIP, this one must be connected, right? End-to-end signaling simply means you have a session, okay, both are stateful, they know what's going on, okay? Oh, I know someone is calling me at this IP, so between your communication, this IP, that traffic is going to be utilizing priority traffic, okay? And nothing going on at the middle part. Dynamic resource reservation means they can decide on their own. There's no special policy indicated, but for priority of the the signaling, there's not much you can do for the middle part lah, right? So the only thing is the edge routers lah, right? Edge routers is going to shape the traffic coming from the LAN where this QoS aware node is. So give priority to the this particular host traffic compared to other traffic, right? At the edge only lah. So any other hop and in between will have no idea, right? So that means because you make a connection, you have a session, it's stateful, there's an explicit end-to-end resource admission control. Per request policy admission control. Per request simply means because of the connection. So they signal the dynamic port number. So port number they want to use, the port number is part of the info required by the priority, okay, to identify the traffic. Resource intensive due to stateful architecture. Stateful because you create a session is always stateful. Stateful here simply means both hosts will be aware of each other, right? Yeah. So it's flow based. So increasing flow means it will still utilize the bandwidth. Nothing going to change. It's just that other data will then have less and less and less bandwidth to use. So it's not very scalable, right? It is at the expense of other traffic. Okay. You can see here the expense is being done here. Oh, sorry, here. It's controlling more and more bandwidth is forwarded from this edge router compared to for the voice rather than others. So others might be queuing up here or lost packet here. Okay. For differential services, there's no need. Okay. The two participating hosts have no awareness of QoS being implemented. It's just simply that the packet will be tagged, right? Inside the header, there was some code to indicate, okay, what priority level, right? And the task of choosing the best path or how each of the hop, okay, will prioritize that traffic is now the decision of not only the edge router, but any of the hop in between, right? So that's why it says manual QoS policy mechanism. Manual because it depends who have this, who is in charge of the routers, right? So different ISP, different organization might put a different set of rules for the QoS. Okay, right? So there's no guarantee because there's no end-to-end session, right? So it cannot enforce end-to-end guarantees because basically tag the traffic, let it loose onto the hop, and the hop will pass along. Hopefully the hop are configured with QoS policy mechanism, so they know how to route the best route, okay, and also the best policy for queuing based on the packet code, right? So you can see hop by hop basis. The QoS mechanism is decided hop by hop basis. Different hop belonging to different ISP might have different configuration, right? So that's why. Right, so it's highly scalable because it don't depend on your edge router. It depends on many other hops in between. It can provide many different levels of quality because you have no control about the hops. So there's no absolute guarantee of quality, but it requires a set of complex mechanisms. So that means all of this might work together. You have to set agreement between them to provide the QoS policy, right? So it requires a set of complex mechanisms to work in concert throughout the network among the various hops. Okay. Right. Any questions so far?
No.
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 Okay. So now we're moving into QoS implementation techniques.
We can categorize QoS implementation tools into three broad categories: classification and marking tools, congestion avoidance tools, and congestion management tools. Under classification and marking tools, session traffic is classified into different priority groupings and packets are marked. Under congestion avoidance tools, traffic classes are allotted network resources. Some traffic may be selectively dropped, delayed, or remarked to avoid congestion. Weighted random early detection regulates TCP data traffic in a bandwidth-efficient manner before tail drops caused by queue overflows, basically congestion, occurs. And under congestion management tools, when traffic exceeds available network resources or we have congestion, then traffic is queued to await the availability of those resources. Common Cisco iOS-based congestion management tools include class-based weighted fair queuing and low latency queuing, or the CBWFQ and LLQ algorithms. If we look at this diagram, you can see the three sets of tools being used in sequence, from the ingress interface on a router to the egress or exit interface of the router. You can see that traffic is first classified and then marked. Notice in the graphic how the packets, before being classified, are all seen here as gray. As they're classified into different classes, they're marked in the IP header, indicated here with the colorization of the different packets. Congestion avoidance is where traffic is policed and selectively dropped. This is where network resources are allotted into different priorities. Packets are put into different queues based on different weights or sizes. The main congestion avoidance tool that's used in Cisco devices is weighted random early detection, or WRED. If queue buffers fill up, packets may be dropped proactively as to avoid congestion. Lastly, we have the congestion management section where packets are put into their queues and are scheduled and shaped based on the network priorities or policies that have been applied. If we look a little closer at QoS traffic marking, we can see that traffic marking happens at both layer 2 and layer 3. At layer 2, we have class of service or COS, which happens using the 802.1q VLAN tagging and 802.1p quality of service protocols. Traffic marking at layer 2 happens on the local area network and is limited to the LAN using layer 2 switches. Under Wi-Fi, traffic marking happens with the Wi-Fi Traffic Identifier field, or TID. With MPLS, you have the experimental or EXP field, also at layer 2. At layer 3, with IPv4 and IPv6, we use the TOS and traffic class fields using IP precedence, or IPP, and DSCP, the differentiated services code point. With layer 3 traffic marking, the marking can go from router to router, and therefore the QoS marking can be carried end-to-end across the network. In this slide, you can see how QoS marking happens at layer 2. We have an Ethernet frame, and the 802.1q protocol can be inserted between the source address and the type length field. You can see the two fields inserted into the Ethernet frame, the TPID field and the TCI field, or Tag Control Information field, which contains a 3-bit PRI priority field which identifies the class of service, or COS marking. The class of service markings have 6 different values: best effort, medium priority data, high priority data, call signaling, video conferencing, and voice bearer for voice traffic. Bits 6 and 7 are reserved for network control information. At layer 3, QoS is implemented in the IPv4 and IPv6 traffic class field. In the older implementation, class of service at layer 3 was implemented using IPP and TOS. The IP precedence is 3 bits, and the type of service is 5 bits, and you can see them there in the 8 bits. The classifications have 8 levels, which map to the layer 2 class of service. You can see there routine, priority, immediate flash, flash override, and critical. Once again, values 6 and 7 are reserved for network control information. The current implementation of QoS uses the differentiated services code point and explicit congestion notification fields, or DSCP and ECN. DSCP and ECN map directly over the 8 bits of the IPP and TOS fields, and the DSCP field is backwards compatible with the IPP field. You can see in this example that an IPP classification of 5 involves the 1 here and the 1 here. If you have IPP and you have 3 bits, then this would be a 4 and a 1, which would be a 5, which would signal a critical flow. Under the DSCP specification, you have 6 bits, 1, 2, 3, 4, 5, 6, and this is a 32, and this is an 8, and 32 plus 8 is 40, so you can see how it would map a 5 under IPP using 3 bits, or a 40 using DSCP using 6 bits. Since DSCP uses 6 bits, there are 64 possible classifications of traffic. QoS marking happens at trust boundaries, and marking should happen as close to the source as possible. Endpoints like voice over IP phones, wireless access points, and video conferencing gateways have the ability to mark QoS packets, as indicated in number 1. Traffic can also be marked using layer 2 switches, as in number 2, or at layer 3 using layer 3 switches and routers. As packets travel across the network, the remarking of the traffic can be necessary. The remarking of class of service values, or IP precedent values, or DSCP values. The main mechanism of congestion avoidance in QoS on Cisco routers and switches is weighted random early detection, or WRED. With weighted random early detection, a percentage of the packets are dropped once we've gone over in a queue the minimum threshold. If the queue has gone over the maximum threshold, then packets are automatically dropped. In this image, you can see the difference between traffic policing and traffic shaping. In traffic policing, when the traffic rate reaches the configured maximum rate, excess traffic is dropped. The result is an output rate that appears as a sawtooth with crests and troughs, as shown in the graph at the top. With traffic shaping, excess packets are retained in a queue and then rescheduled for later transmission over increments of time. The result of traffic shaping is a smooth packet output rate, as shown in the bottom graph.
All right, so that was a brief, description just now about traffic shaping and packet traffic policing. So there are two different things, yeah. Policing basically just simply drop, whereas a shaping will allow the excess packets to be rescheduled. That means the excess one will be put into a different buffer lah, so that it can be rescheduled to send out of the router. So shaping, in my opinion, is much better compared to policing. Right. So let's look at this avoiding packet loss. Whenever we have packet loss, okay, last time we used to think about, congestion cause packet loss. Okay, why is it? Congestion simply means that the intermediate devices, okay, cannot handle the amount of traffic coming in order for it to send out at the same time, right? So if the space is not available for it, so it's simply drop it lah. Yeah. So drop causes if it's a TCP, it will cause retransmission. Retransmission cause latency, slow, right? Slows down the transfer of data, because retransmitting means still waiting for the confirmation or acknowledgement of this transmitted data. So that's why it's slowed down. So it's actually causing how congestion can basically cause slowdown, right? So to prevent this packet loss drops, right? Packet loss or drops, same thing, yeah. So increase the bandwidth, the link capacity means the bandwidth, increase that, okay? So the more you can send in, the less you have to queue up, right? That means you can send more at the same time, means less time for the packet to remain in the queue, so the queue can be freer, right, for longer, right? Then also you can do packet loss, reduce packet loss also by guaranteeing enough bandwidth. Okay, at the intermediate device, the cost of congestion and pocket because congestion, right? The cost of packet loss is by congestion can be reduced by simply increasing your buffer space. Means put more RAM inside your router, right? So this is especially good for bursts of data incoming, right? So guarantee enough bandwidth by doing that, increasing buffer space. Okay, can use WFQ, CB, WFQ, and LLQ, priority queue, to provide prioritization. Okay, for application that is drop sensitive. Means if you empty the queue under this LLQ or under any of this QoS faster, okay, that will increase the storage of incoming packets, right? Thereby reducing packet loss thereby satisfying drop-sensitive application. So the priority basically allow the queue to be emptied faster. Okay, but that means it will occupy the bandwidth more at the expense of other traffic. Other traffic might be maybe experience more packet loss, right? But because they are not critical, then it's okay. Okay, consider as a sacrifice, lah. Okay, right? So that's what happened. So drop lower price. Another thing is you can also, if you need to drop, is you drop the low priority packets before congestion occur, right? So there's a queuing mechanism called WRED that starts to drop low priority packets before congestion occurs. That means it is actually kind of predicting the traffic. If it detect that it starts to congest up, then it will start to drop low priority packets. Okay, because low priority that means it will provide more bandwidth for the other priority queue, right? So it will occupy the more of the bandwidth. So need to drop the low priority packets so that less of them will occupy the bandwidth, so we can give more towards the priority packets. Okay, so it's a balance lah. You have to sacrifice the low priority packets compared to the high priority packets. Right, so QoS tools, just now we saw done in sequence, classification and marking. Basically, this is the one that mark here simply means placing or toggling bits at the appropriate bit section, right, to identify the packet, right? And then congestion, basically classifying the traffic. Okay, so then here is where we can do some selective, depending on the priority of the packet, selective dropping, right, to avoid congestion. So that's where the WRED is here, WRED. Okay, and then congestion management tools, traffic will be queue. This one is where you either use the policing or the traffic shaping, right? Right. So traffic is queued to avoid availability of resource. Excuse me. So this is shown here in this. So I think the guy already explained this one to us. So basically the same explanation, but now you will see it in terms of graphical format. Excuse me. Where these are incoming packets is classified, and then once it's classified, the appropriate bits are marked onto the header, and then selective dropping is done, right? And if it's beyond the queue cannot support, then it's dropped. Simply drop, yeah? And then it's queue up based on their priority, and then it's scheduled to be released and also shaped, right? So shaping basically allow, even though the ingress is bursty, okay? Bursty, yeah? The shaping here and scheduling here will reschedule the release so that it's not bursty. Okay, so to prevent jitter, because this is at the source. This is at the source. Jitter happens at the destination. If jitter happens because of bursty data incoming, right? So to prevent bursty data, we shape the traffic here, right? But remember, this happens not only for the distributed one, the IP version 6 and also IP version 4, but mostly for IP version 6 differentiated service, right? This happens on all the routers in between, all the hops in between source and destination. All right, so classification and marking. Okay, so it basically marking is happen on layer 2 and 3. There are specific fields in both in frame and packet, right? So here we identify the layer, okay, and the QoS tools operating on that layer. So under layer 2, data link layer, we have the normal wired Ethernet and also the Wi-Fi and the MPLS, right? Okay, and the marking field identified in their header as class of service for Ethernet wired Wi-Fi traffic identifier, or TID for Wi-Fi frames, and then experimental for MPLS, right? For situation where it is your router that's responsible to do the marking, yeah, that means you're marking at layer 3 because router is at layer 3, right? So we use the older one, which is IP precedence, okay, or the newer one, which is the differentiated service code point, right? This one actually differentiated service is actually meant for IP version 6. It's also available in IP version 4, but IP version 6 fully utilize this already. Okay. Right. So here you can see, as explained before, inserted into the frame, okay, between SA and TL, you have TPID and TCI, right? And then you can see that they is part of the VLAN, right? ID here, and then you have the PRI, okay? PRI, this is at layer 2, right? Class of service, okay? And then 3 bits used for QoS, okay, which is at 02.1p. This is at 02.1q for VLAN ID tagging, and then at 02.1p for PRI. Okay. Right. So what can we put inside? Okay, we can put this is the value in decimal, this value in binary, 3 bits, right? So each of the 3 bits pattern indicate what kind of class that traffic is, that packet is, so or frame in layer 2, right? So best effort and so on until to reserve, right? And then this actually will map to, because they should be the same, right? The traffic, whether it's encapsulated in frames or in packet, they should match, right? If it's traffic for audio at 2, should be matched at traffic for audio at 3, right? Or else mismatch means there's an error already, huh? So at 3, depending on where you want to implement the marking, yeah, if it's at layer 3, yeah, at the router, then you look at this. So the type of service for IPv4 or traffic class, the names are changed, right, in IPv4, but their usage is the same. Okay, right. So type of service and traffic class field, okay, as indicated, if you're using the older ones, okay, older IPP, you got 3 bits and unused 5 bits. This one again mapped to the new, because it's the same at bits. Okay, the type of service or traffic class in IP version 6. So in IP version 4, right, it still use at bit, and the traffic class also use at bit. And the way the map, even though it's IPP 3 bits and unused 5 bits, these 3 bits will map, okay, to 6 bit, and the meaning in terms of the binary value and the meaning is the same, right? That's what it is indicated, right? So basically that is here, right? 3 bits, the code 3 bits code, each pattern will mean what kind of traffic. But as you look at, if you look at it as a DSCP 6-bit, then of course the value in terms of binaries change, but it maps to the same usage of classification, right? So that's how they basically enable future capability, because the 6 bits can differentiate more than 3 bits, more patterns basically. Okay, just that the pattern that can match with the 3 bits should be the same, and then future patterns, okay, up to them to implement, right? All right, so these are the patterns for the 3 bits, okay, and should map to the pattern for the SCP. All right. Here talk about that, right? This DSCP values, assured forwarding values shown in the figure, right? So low drop, medium drop, high drop. This differentiate between different classes. So depending on their class drop type, then the possibility to be dropped increases, right? Then class selector bits, best effort, medium priority, high priority data, call signaling, video conferencing. Again, this value should map to the 6-bit, 3 bits value should map to 6 bits. Okay, so you just basically, because these are on the left hand side, so you increase on the right hand side 00 bits. So basically 5 map to, this is 40. So 40, and the thing to know here is that no matter what is the pattern, okay, it will map to the same meaning. Okay, so if 5, this one, voice via voice traffic, so this will map to 40, also map to voice traffic, right? So the marking is done on a different layer depending on where you want to put the marking. So in LANs, because we work on frames, so layer 2 will apply. So both endpoints and switch, because they are because when you're transferring frames from endpoint, although your endpoint can go all the way to application layer, but because it's operating inside a LAN where frame is being used, so the marking is done on frames, okay, for endpoints and switches. For multi-layer switch and also router, because on layer 3, the marking will be done on layer 3, okay, network layer. All right, right. So that's marking, and then we go to congestion avoidance. Congestion avoidance using WRAD, all right, weighted random early detection, right? So this help us to avoid congestion by managing the buffer, right? Whether they want to slow down the TCP traffic, to throttle back, they want to make sure the buffers are not exhausted, right? So by managing the buffer, they hope to, or WRAD hope to avoid any packet loss by tail drops. Okay. But if it does drop, okay, it will look at the minimum threshold, right? So minimum threshold, there are no drops. Then between minimum and maximum threshold, then a slight percentage will be dropped, not all. But when the maximum threshold, this is the point of no return, then all packets will be dropped. Okay, so this is the WRAD task to avoid bottlenecks before the congestion becomes a problem. So we stop the congestion at the source, basically, right? At the source. And then as we move towards another router, and that router also will employ WRAD. Again, before the next segment of network, experience congestion, it will do the same thing again. Obviously, dropping will, for UDP, of course, is gone, right? So that means you experience lost packet. For TCP, retransmission will still happen, okay, with the lost packets, okay. But it is managing so that the traffic jam is not become a gridlock. Like at least traffic is still moving, okay. Right, so talk about shaping and policing. The rate, the lines here just indicates the rate of traffic arriving, right? So arriving, this will be bursty, all these sharp peaks. The trough means like going down a trough here, okay, depression here means the traffic is low. And this line indicates the line of no return, that one. So for example, for WRAD, if it sees the traffic go beyond the line, those excess traffic will be cut, right? Will be cut. But for traffic shaping, this excess will be put into buffer, into buffer, a queue, right? And to be released once there's a bandwidth, okay? There's a bandwidth, available to transmit. So network shaping is not as bad. The network shaping will not drop too many packets, basically. But for policing, it's basically to drop, okay, to drop. So there's no opportunity for the excess traffic to be sent. So you can see here is basically less packets coming in. So basically, right, as the time move, right, so this excess will be slowly making use of this excess bandwidth here, right? Excess bandwidth here. Put this into buffer. As time move, it will move. So put inside those excess. Make use of the time in space that there's less traffic. So you will see something like a smoother transmission, right? Whereas here, there's no opportunity at all because you don't delay, you don't schedule, you don't keep, you just cut. This traffic, excess traffic, will be dropped. So you see some kind of this like a very cut off point graph. Okay. Right. So QoS policy must be able to consider the full path from source to destination, right? For ensuring best experience for end user, enable queuing at every device in the path between source and destination. Just to remember, this queuing is the latency that happens at the intermediate device. Because queuing, buffering, and scheduling and network shaping, it introduces latency, right? So it does add up, but there's no choice for ensuring smooth traffic flow without congestion. So you have to suffer a little bit of latency, right? To ensure that, right? Perform classification and mark the traffic as close to the source as possible, because traffic policing or shaping as close to the source possible ensure the remaining bandwidth, because what we're doing, okay, before the packet egress or frame egress the device is to ensure there's no congestion. That means if you try to avoid congestion as close as the source possible, then the remaining path will not experience congestion. So that's why as close as possible to the source as possible. Source here means the source data source typically mean endpoint, right? So and also the shaping and the police traffic flows as close to the source as possible. Thereby you can see the classification, the marking, the shaping, all this are actually in the same device, happening in the same device, right? Okay. Right. So any question?
No.
No.
No question.
All right. How about you, Kelvin? No. Oh, type already no. All right. So I'll stop recording now. Okay, we finish this chapter. Right. So we'll take a quick break before we move on into our tutorial. Right. So let's move to our tutorial meet.
Oh, okay.
Right. Move to our
Okay.
yeah. Hello everyone. Let's take a 10 minutes break. It's been a long lecture, so we'll resume. Now it's 3:15, 10 minutes, 3:25, okay? We resume at 3:25. A quick break. Hello, everyone. Oh, I forgot to upload the lecture notes, is it? Okay, I will upload it, Calvin. Sorry about that. All right, so 4 p.m. already, yeah? Okay. I went through back and I see that a lot of it not marked, so I will make sure that it's marked by next tutorial, so and then I can give feedback on next tutorial. Right, so I'll put in message. I noticed that Noel put in red question comment. I make comments also already. I will go through them one by one. All right, so 4 o'clock already. So okay, thank you everyone. So Noel can remain. All right, Noel can remain. The rest can dismiss already. Thank you, Farah and Kelvin.
Okay, sir. Thank you.
All right. Okay, Noel, we can do our